everybody, this is Miss Bufford, and in this video we're going to talk about calculating wavelength, energy, and frequency. So your learning goals are to be able to perform calculations of energy, frequency, and wavelength. So in the last video we talked about the relationships between these three variables of electromagnetic radiation, so that wavelength, frequency, and energy. And we talked about the fact that frequency and energy have a direct relationship with one another, and that can be shown in an equation that contains both frequency and energy, which is this one right here. So as one variable is increasing, the other is increasing, and the same could be true if one is decreasing, then that same variable is decreasing as well. And we can see that relationship up here in these two arrows as well. The inverse relationships that exist between these variables exist between wavelength and frequency. So we can see that in this equation right here. They're inversely related to each other. And then we've got another inverse relationship between wavelength and energy right here. All right, we can see that here up in the arrows because as wavelength increases going this way, both of these variables are going to be decreasing. All right. So I just wanted to point that out. One other thing I'd like to point out is that when we're performing these calculations, let's say we're given a very specific wavelength, and that wavelength just happens to fall about here. So we'll just say that that little red line that I just drew is equal to a specific wavelength. Well, that specific wavelength corresponds to a specific frequency and a specific energy. So anything without any amount of electromagnetic radiation that has that wavelength will be a certain type of electromagnetic radiation that also corresponds to a very specific frequency, which will always be that frequency, and a very specific energy, which will always be that amount of energy. All right, so if I've got a really tiny wavelength down here, it's going to correspond to something with a high frequency and a high amount of energy, a very specific amounts of energy. All right, so let's go ahead and talk about the calculations. So these equations that are listed over here, these are the equations that we're going to be using for all of the calculations that we're going to be doing in this building block. So I've made a little toolbox, and we've got our equations, and for each equation there's a list down here of the different variables of what they are. So we've got energy, which is capital E. We have a number called Planck's constant, and this is just a value that is always going to be equal to 6.626 times 10 to the negative 34 joule seconds. So it's got units of joule seconds. So this is a constant. It's always got that value. So anytime you see the little h in one of our problems, you're going to use this number for Planck's constant. All right, and then V is representing frequency in our calculations. Sometimes you'll see some sample problems here and there or online where people are using F to represent frequency. So if you see that used for frequency, don't get too confused about it. But we're going to use the little v. Frequency has units of hertz, but really what hertz are is just 1 over seconds, or that can also be written as seconds to the negative first power. So if you see any of those, they all mean hertz. They mean the same thing. If you're reporting an answer in frequency, let's say your problem is asking you to calculate the frequency of something, then you really need to give the unit in hertz. But if you're using frequency in a calculation, like that's the known variable that's given to you and you have to plug it into your problem, I would recommend using 1 over seconds because it makes it a lot easier for you to see how the units are going to be canceling out with one another in that problem. So that's just some ways that you can use those units. The little c over here represents or stands for the speed of light, which is also another constant value. So the speed of light in a vacuum is 3.00 times 10 to the 8th meters per second. And that's the number that you're going to plug into the calculations anytime you see the little c. And then this lambda symbol right here that represents wavelength in meters. So remember that wavelength always must be entered into our calculations in meters. And when we're calculating a wavelength, the answer is always going to be given to us in meters. So there are going to be times when we're given a wavelength in nanometers and we'll have to convert it to meters in order to use that value in our equation. So just keep that in mind, that wavelength always needs to be in meters when we're using these formulas. All right, so let's go ahead and talk about the steps for solving these problems. So you're going to be given a word problem, and we're going to go over 3 examples in this video when I'm done talking about all this stuff first. So the first step is you want to identify the information that's being given to you in the problem. So this could be wavelength, frequency, or energy. So you could be given any one of those pieces of information. And then you want to identify what the question's asking you to calculate. So is it asking you to calculate wavelength, frequency, or energy? Right? So you'll be given one of these 3 variables, and you'll be asked to calculate the one of the other 2 variables that's remaining. All right, so the next step is to determine which one of these 3 equations you're going to need. And the way that you do that is you want to look at the equations, look at the variable that you're given, look at the variable that you're being asked to find, and look for an equation that has both of those variables in it. You need to have both variables present in the equation that you choose to use. Then you want to take a look at that equation, and it may need rearranged. All right, so whatever you're solving for or looking for needs to be what the equation is equal to. So in this case, for this equation down here, we would be solving for energy, since energy is by itself. So whatever your unknown variable is needs to be by itself on one side of the equation so that it's set up to solve for that unknown variable. All right, and then you're going to need to perform any conversions that you might need. So if you're given a wavelength in nanometers, you're going to have to convert that to meters before you can use it in that calculation. So step 5 is to perform any conversions that you might need. So the units that you're plugging into these equations, they all have to match the units that are given here in this list of variables over here. And then the last step is just to take the values you have and plug them into the equation and solve it. All right, so let's first, we're going to talk a little bit more about converting between meters and nanometers. I'm going to show you an easy way to do it. And then we're going to do our examples. And so when we're converting from nanometers to meters, there are 2 ways you can do it. You could choose whichever way you want. You could use dimensional analysis like we learned in Unit 2. This is method number 1. And you want to have this table available to help you so that you can see what the conversion factors will be. But in this case, we're converting, for this practice example here, we're converting 490 nanometers to meters. And so we're going to start with 490 nanometers. And then I know by looking at this table down here where nano is, I know that 1 base unit is equal to 0.000000001 nanometer. And so I'm going to use that conversion factor. So 1 nanometer is equal to that many meters. All right, and I should have put my unit up here. I should have a little m there. All right, so then I would just plug that into my calculator, and I would get this wavelength here in meters. All right, 4.9 times 10 to the negative 7th meters. Or I could do a super easy thing, and I'm just calling it instant conversion because that's kind of like what it is. Since I know that nano means 10 to the negative 9th, then I can replace the little n in my unit with a times 10 to the negative 9th. And this will tell me, it'll give me the same answer. It looks different, but the only reason it looks different is because it's not really written in proper scientific notation. You could use this number just like this in your calculation. It's not going to make any difference to your final answer. So normally when I do it, I just replace that real quick, use this number right here in my calculation, and that's it. But sometimes you need your final answer to be written in scientific notation, or you just if you are doing this calculations and you're getting a number like this, but expecting a number like this, that's where I've seen some confusion with this method of conversion. Just understand that if you're getting an answer with times 10 to the negative ninth and you've got this big number right here, then it's the same as this. And all we've done is move that decimal place over 2 spaces and then adjust our exponent. So this is a super easy way to convert, but you have to understand that these two things mean the same thing, but this is the proper way of writing this number in scientific notation. All right, so now that we know how to do some quick and easy conversions between meters and nanometers, let's go ahead and do some practice examples. So example problem number 1 says, a photon of light has a wavelength of 422 nanometers. Calculate the frequency of the light. So the first thing I'm going to do is I'm going to identify what information is given to me in this problem. I'm given a wavelength. All right, so here's what I'm given, 422 nanometers, and it's asking me to calculate the frequency of this light. So the next question is identify what the question's asking you to calculate, and that's going to be frequency. So the symbol for frequency, or the variable here is little v, so I'm looking for frequency. All right. That's what I'm looking for. Step 3 says determine which equation you're going to need. And so remember, I'm looking for an equation that has both what I'm being given, which is wavelength, and that's lambda, and frequency, which is v. So I'm looking for lambda and v in the same equation. So if I look over here at these 3 equations in my toolbox, I'll notice that this equation right here has both frequency and wavelength in it. All right, so that's going to be the equation I'm going to choose. And the next step says rearrange the equation if needed. So I'm being asked to calculate frequency. That's my question mark. And since frequency is already by itself on that one side of the equation, I'm not going to need to rearrange anything here. So no rearrangement needed. And then I need to see if I need to perform any conversions. So I know that I have wavelength here, and my wavelength is given to me in 422 nanometers. So I am going to need to convert that. So what I'm going to do is I'm going to write 422 times 10 to the negative ninth meters. And there's my conversion. Remember, I just basically switched out nano for times 10 to the negative ninth. All right, and since I'm just going to plug this straight into a calculation, I'm not going to worry about putting it in proper scientific notation for right now, so don't worry too much about that right now. If you were reporting it as a final answer, then yes, you would need to convert it to proper scientific notation. All right, enter the values into the equation and solve. So that's our last step here. So I just need to, remember I'm using this equation here, and V is my unknown, so frequency is my unknown. The speed of light, so C is the speed of light, so I'm going to write 3.00 times 10 to the 8th meters per second. And my wavelength needs to go on the bottom, so 422 times 10 to the negative 9th meters. And then I just plug those into my calculator. And when I'm plugging these values into my calculator, they're numbers in scientific notation. And so you want to use the E function. Don't use the little times 10 and then use the caret, because then your calculator treats that like separate operations, and it doesn't treat it like a number in scientific notation. So in your calculator, what you should type is 3 and then the little E button. It looks like it says double E on your calculator. It's EE, but it only puts one E on the screen. And then 8. And then you're going to divide that by 422 E negative 9. So this is what it should look like in your calculator right here. All right, then you hit enter. And we end up with 7.11 times 10 to the 14th. And since we're calculating frequency and we want this is a final answer, I'm going to use the unit of hertz. But if I'm checking through my work to make sure to see that I've set everything up correctly, I have meters in the numerator of this unit right here, so it's like in the numerator of the numerator. And then I have meters in the denominator down here, so meters will cancel out, and I'm left with 1/seconds, which is hertz. All right, so that's a good way to make sure that you've set everything up correctly and you're getting the unit that you expect to get. All right, so there's the final answer. We do want to take into consideration significant digits in these calculations, and in this case, for this particular example, remember when we're dealing with numbers in scientific notation, the values that are in the coefficient are the ones that we look at. And since we're dividing here, we want to go with the fewest number of overall significant digits. And they both have 3. So I have 3 significant digits in my coefficient here. All right. So let's go ahead and do another example. For this one, it says the problem says, what is the energy of a quantum of light with a frequency of 7.39 times 10 to the 14th hertz? So this problem has a lot of fluff in it. And what I mean by fluff is it's got some words in there that might throw you off and make you feel like you have no idea how to solve this problem. In reality, all you have to do is just follow the steps, identify what information is being given and what information you're being asked to calculate. So if I ignored the information about the quantum of light, which is a photon, it's just another fancy way of saying a photon. If I just ignore that, step 1, I'm going to identify the information that's being given to me in the problem, which is frequency. So I have a frequency of 7.39 times 10 to the 14th hertz. So there's the information that's being given. And so now I need to identify what I'm being asked to calculate. I'm being asked to calculate energy. It says, what is the energy? So energy is my question mark here. All right, so in the next step, determine which equation we're going to need. So I need an equation that has both frequency and energy in it. So I'm going to look over here at my toolbox, and this equation has both energy and frequency in the equation. And so the next step after that is to look at that equation and decide whether I need to rearrange it or not. So I'm being asked to find energy, so that needs to be all by itself on one side of the equation in order to solve for that unknown variable of energy. And it's already written with energy on it all by itself, so I don't need to do anything to this equation. It's just great how it is. So score. All right, perform any conversions needed. I don't really need to do anything here. My frequency is already given to me in hertz. Energy is just a question mark, so there's no unit on that just yet until we do the calculation and then we get our final number. So I don't have to do any conversion with this problem. And then I just need to take the numbers I've got in that equation and put it all together. So I know that energy is equal to Planck's constant. Remember that little h is Planck's constant, and it's always going to be equal to this value right here. So I'm going to have 6.626 times 10 to the negative 34th joule seconds. So there's that number. And I'm going to multiply that by the frequency that's given to me in the problem. So 7.39 times 10 to the 14th hertz. And since I'm using frequency in this as a calculation here, I'm going to get my eraser out for a second. All right, since I'm using frequency in my calculation, instead of writing hertz, I'm going to use 1/seconds, and that's going to allow me to see how my units are going to cancel out a lot better than just using hertz. All right, so if I were to plug this into my calculation or into my calculator, I would get energy is equal to 4.90 times 10 to the negative 19 joules. All right, and so again, when I plug this into my calculator, make sure you're putting 6.626 E, and it's not even the little e, I don't know why I keep writing that, negative 34, and then you want to multiply that by 7.39 E to the 14th, or E14, and then just hit enter. All right, so in your calculator, that's how you want to put it. And then again, we want to pay attention to our significant digits. So I'm going to look at those coefficients. I have 3 significant digits here, and I have 4 here. So my final answer should have 3 sig figs. So there we go. I got my 3 right there. So this is my final answer. All right. If you have any questions about this example, go ahead and put it in your notes. You should be putting these examples in your notes anyways. These are listed on the notes outline for this building block. And now let's go ahead and do our last example. All right, so the last example, problem 3, says calculate the wavelength in meters of a radio station that broadcasts at 100.4 megahertz, right? So the steps to solve this problem are, so I have to identify what information is being given to me. So I have a frequency, and I know that it's frequency because the units that are given are hertz. So let's see, I don't want to use the megahertz because that's not a unit that goes with these equations over here. It has to be in hertz, so I'm going to use this really big number here. I've got 100,000. All right, and that's hertz, right? And so that's my frequency. So I'm being given frequency, and it says identify the question, what the question's asking me to calculate. Well, it says calculate the wavelength. So I'm looking for wavelength, and it specifically says in meters. All right, so I'm calculating the wavelength in meters. So wavelength is what I'm looking for, and it should automatically give me the wavelength in meters. That just means don't convert it to nanometers or something else. All right, so the next step, determine which equation you're going to need. So which equation has both variables in it. So I'm looking for an equation that has both wavelength and frequency in it. And it looks like here's my equation that has both wavelength and frequency. And so now I need to decide whether I'm going to rearrange this equation or not. And it actually looks like I will need to rearrange the equation this time because instead of being set up to solve for wavelength, it's set up to solve for frequency. And it's always easier, I think, to rearrange these equations before you plug in all the numbers. It's a lot less writing. And so I'm going to go ahead and rearrange this equation. I've got frequency equals the speed of light over the wavelength. And in order to get wavelength on the other side, I have to multiply both sides by wavelength. So I'm going to multiply both sides by wavelength. That will cancel out on this side. And then I need to divide both sides by frequency. So I'm going to divide this whole thing by frequency. That's going to cancel out frequency on this side. And so I basically end up with wavelength equals the speed of light over the frequency. All right, so this is the equation that I'm going to use. All right, so now I need to perform any calculations if I need to. And for this problem, I am not going to need to perform any conversions or anything like that. So I'm going to X that out. And enter values into the equation and solve. So what I'm going to do now is I'm going to take the variables that I've got. So I have my wavelength, and that's equal to the speed of light, which again, the speed of light is listed right over here. It's a constant, 3.00 times 10 to the 8th meters per second. And I'm going to divide that by the frequency. And again, I'm going to put this in here as 1/seconds because I'm putting the frequency into a calculation and I want to be able to see what's going on with my units. And so in my calculator, I want to type 3.00 E8 divided by the frequency. Right? Then I'm going to get a wavelength equal to 2.99 meters. Right? And I just want to make sure that I did my significant digits correctly. So I'm looking at the coefficient here for the speed of light has 3 significant digits. This number right here has 4 significant digits, and so I should have 3 in my final answer. So wavelength is equal to 2.99 meters. I hope these example calculations were helpful. If you have any questions, remember to go ahead and write them next to the examples in your notes, and we can talk about them in class. And I'll see you guys then. Thank you for watching Buffered Chemistry. Subscribe to my YouTube channel for more chemistry help.